So what I want to do with a more complicated example is to reproduce one of the effects that's available in Cinema 4D. And I've got Cinema 4D open here. And it's an effect which is used wonderfully in the video No Keyframes, which is available on Vimeo. And it uses one of the MoGraph effects that comes with Cinema 4D. And we can see it here. We've got a large number of blocks resting on a plane, and as I play the simulation, the boxes rise up into the air, and then at a certain point they start to be simulated by the RBD simulator and fall down in a chaotic fashion. And I want to demonstrate how we might achieve a similar effect in Houdini. So we want to reproduce that effect we've just seen in Houdini. And rather than do this step by step, I'm just going to concentrate on the dot network parts of achieving that. So I've already set up here a set of boxes and something I've called an effector. And an effector is combined with some nodes that I'll show you in a minute here in the points object, enabling us to change the position of these boxes as this object, the effector object, moves through them. So how's this achieved? Well, first of all, let's have a look at the effector object. And I've added an extra tab here to the effector object with some parameters for inner radius, randomness, strength, control type, and we can either have this as a sphere or a box, and then a ramp which controls how strong the effect of this is between the outer edge of the sphere and the inner radius here. Now the effector is in fact just a set of control nodes which are then managed by a switch here which changes depending on whether we have a box or a sphere type of control. And what a control node allows you to do is to create various types of control graphics. These won't render, and they also they won't render because I've got a null here with the render flag on it, and also they aren't shaded in when you've got a smooth shaded mode. They still appear as wireframes, and you've got various choices here as the type of icon you want to create. So by combining these with some transforms and some merges, we create this guide geometry here for the sphere or the box. And the inner radius here controls the size of the inside sphere, and obviously the outside sphere is controlled by the global radius like that. Let's have a look at the points node, and all we do here is construct a grid, create some point normals, which we can see here. I've got point normals switched on. Then we use an add node to delete the geometry but keep the points. We don't in fact probably need to do that, but it enables us to visualize things more clearly. And then I've created a subnet where the meat of what we need to do is done. And then I've added a null which marks the point at which our points are being output from the subnet. And then finally I copy a box which I've object merged in here to each of the points. So let's have a look in more detail at the subnet. I've added some additional parameters to the subnet. First of all, I've just brought in the position, scale and rotation of the effector object, and the effector is specified here in this parameter, and then I'm just taking the values from which we saw earlier, which were specified on the effector node itself. They are tx, ty, tz of the effector. So if we go up to the effector, we can see that the translate values are tx, ty, tz, rotate rx, ry, rz, and scale sx, xy, and sz. So what I've done here is use channel functions, and let's have a look at this one. CHS and then effector. What is this doing? Well, CHS produces a string value from a channel, and the channel we are specifying here is on this node. That's what the dot and the slash means, and it's called effector. And in fact, it's this parameter here. So this brings in this string here, and then we add slash tx to it, and then we pass that into a channel function. So what this is doing is grabbing the tx parameter of the object specified up here. Similarly, ty, tz, the scale sx, sy, and sz, and rotation similarly. Let's have a look inside. Well, the first thing I do is to transform the incoming points here. And the reason that we're doing this is that we are inverting the transforms on the effector object. And the reason that we are doing that is so that we can assume that our effector is of unit radius, which makes the calculations later on much easier. So if we transform all of the points using the inverse transform of the effector object, the effect is to recreate a coordinate system where the effector object is of unit width or unit radius. So let's now see what we do next. What we do next is have two attribute create nodes, and these are creating an attribute called weight. And I've got two nodes because the way we do this depends on whether the effector is a sphere or is a box. And the extra parameters that I've added here give us the inner radius, which we're just collecting from the effector object. This gives us the value which we need to use to transform that into something which can be fed into the ramp. And the len, which is the key parameter, tells you what you're going to feed in for the value into the second part of the ramp. And the length in the case of sphere is of course simply the center from the origin. That gives you the length. We then transform that so that it has a range of 0 to 1 between the inner and outer radiuses of our sphere. And then finally we draw on the ramp on our effector to adjust the weight. For a box, this is all the same, apart from the fact that the length is the absolute of tx, ty, and tz, as you can see here. Then this switch simply switches based on whether we are using a box or a sphere as our effector. Now, I use an attribute copy to move the weight back on to the original points that were coming in. And the reason I do that is I don't want to use our transform points anymore. The only purpose of transforming those points was to calculate this attribute. An attribute copy simply copies according to the point number, so it takes the value of the weight for each of these points and passes it into the point coming in here, which has the same point number. Then we adjust the weight, and that is because we want to add some randomness, and we take the randomness value from the effector again. Next we move the points, and we move them by the amount specified in our subnet for position change. But we multiply that movement by the weight attribute that we've just created. And for rotation we have to do something much more complicated. First of all, we create a rotation attribute, and again this is just the parameter here for rotation change multiplied by the weight. But when we come later on to use the rotation attribute in our copy SOP, it expects the rotation attribute to be a what's called a quaternion, which is a 4-value vector which takes into account the order of rotations. So unfortunately this won't do. What we need to do next is create a small VOP network, which I've done here. And all this does is bring in our rotation attribute, use the Euler to quaternion node to convert it into quaternion, and then add an attribute which we're calling rot. So at this point we have a rot variable, and then I use an attribute node to delete the rotation attribute which we no longer need. Then we create the scale, which is similar to the creation of the rotation attribute, except that of course we want the scale to be 1 when the weight is 0, so we need to add on this extra factor here. Then, this is important later when we come to bringing this all into DOPS, we compute the velocity of the point using a trail SOP. And then finally this final attribute SOP is not actually needed, so I'll delete it. So we then copy our boxes onto the points. Now we could see that the points have moved because we moved them here using this point SOP. So that explains why they're moving when the effector gets close. What happens if I was to, for example, have a scale change so that they became twice as big when the effector was near? Does that work? Well, let's put the display flag there and then have a look, and we can see they get bigger and smaller. Well, why is that happening? Well, the answer is that when our copy SOP operates, it looks for attributes on the points called scale and rot in order to determine the rotation and the scale of the copies. So in this case what's happening is it's finding the scale attribute which we put onto these points, and when it copies the boxes it's taking that into account. And that will similarly work for rotation. If here I make our boxes that are affected rotate by 45 degrees, and I'll revert this back to its default, we can see that the boxes rotate as the effector passes over them. Begin the process of creating a DOP simulation which will switch between the animation we've just created using the effector and a rigid body simulation. First of all, I'm going to create a ground plane, and the next thing I'm going to do is move the display flag in my points object to this null points out, and that means I've just got the points. I'm also going to turn on the display flag for the box object so that we can see it. And I'm going to create something called an RBD point object. An RBD point object asks you for a set of points, which are going to be these, and an object to copy to them. So if I select this, I'm going to select the points. In fact, let's do that manually. And then I'm going to press enter. And then I need to select the object instance, which is the box. And we can see that we have a copy of that box at each of the points. And that's a copy of an RBD rigid body box. So when I press play, after it's finished calculating the SDF volume that it needs to do the RBD simulation, these boxes should all start falling onto the floor. And indeed, that's exactly what happens. But as you can see, the effector object no longer has any effect. And the reason for that is that the information in these points is only being used at the first frame to set up our simulation. And then after that, it's irrelevant where these points are or the attributes that we have attached to them. So the next step is to look at how we can use the attributes here on our points to affect when the RBD simulation kicks in. So let's see first of all how we can bring the animation that we've got on the points into our DOP simulation. So let's go into, let's lay this out, press L, and let's go into our auto DOP network. And I'm going to maximize this. Now, from the earlier part of the tutorial, we learned about the keyframe active node, but that works on individual objects, and in this case we've got a whole array of objects, so it's not going to be possible to use that to bring in the animation. Instead, we need to use something called the point position node. And a point position node allows us to bring animation in from points. So first of all, let me select the points using this selector here, and we want to select points out. The time is going to be the simulation time, ST, and of course, since that's going to change at every frame, we must set this always. We're not going to use a point group because we want to use all the points that are being brought in here. And then we have this option for the point number. And what this does is associate with each of our objects, which are coming through here, and we've got probably, here we are, 100 objects, a point number from these points here, which is going to be used to bring in the position, rotation information and so on for that particular point. So let's have a look and see what we can use for the point number. And I'm going to bring up a details view. And if we have a look at one of our objects on the details view, we can see that it has this information here, this data container called copy info. And one of the things that there is in copy info is the copy number. And since we've used the exact same points, set of points, to create our point object here, this copy number is the number of the point that was used to instance this particular RBD object. So in this case it's 0. As it happens, the next one will probably be 1, and so on. So we can use this bit of data, the copy number, for the point number in our point pos node. So let's just do that. Again, we're not going to need to set this at every frame because it's going to stay the same. How do I get access to this data that's sitting here? Well, I'm going to have to use the DOP option function. So let's maximize this. And the DOP option function is DOP option. And then the DOP that we're in, which is $DOPNet. The object that we're dealing with, which is $ObjID. The subdata name, which is copy info. And then the field name, which is copy num. So what this should do is give a different point number for each of the objects that's passing through this node. And for the moment, instead of putting these into the standard position data, I'm going to put them into my own container, which I'm going to arbitrarily call point position. You could call it anything that you want. And what this should do is bring in the position of those points at each frame. and put them into a container called point position. So let's play the simulation through. In fact, first of all, let's have a look at our scene view and have a look and see which objects are the ones that are going to be first affected by our effector. And I can do that by hitting the D key and selecting Show Object Names. And then if we zoom in here, and it'll probably be a bit easier if I switch to the wireframe view, we can see that, for example, points 95 is this object here, which is right near the edge. So let's play our simulation. Now, for the moment, of course, this point position is not going to have any effect because we're not using the data that we're creating with this in any way. But when the effector gets to here, what we should be seeing, let's just stop it there, is on our details view. If we go to object 95 and we go to the point position, we should see, there we are, that it's bringing in a position, and we're also getting some velocity information here, and that means that point is moving. That velocity information is being taken from the velocity that we calculated back on the point out here, where we used a trail to calculate the velocity here and create the V attribute. So that is being brought in to our auto.network. Okay, so we've got the points, position information and so on in here. What do we then do with it? Well, there's a solver in Houdini called the copy data solver. So let's lay one of those down, and I'm going to connect this instead of our RBD solver. Let's disconnect that. So now we've got a copy data solver. And what a copy data solver is, simply moves data from one container to another. So if I take my point position and then copy it into my position data, then at every frame the position will be updated with the position data that we've imported using the point pos. So what should happen now is that our blocks should be animated using the point position. In other words, let me just get rid of the names. In other words, they will be and there we are, we can see they're animated, but there is something going wrong here, which is that our objects are embedded in the ground plane in a way that they weren't earlier on. The reason for that is that by default the point pos node doesn't take account of any transform at the object level, and in fact we raised points up initially, so I need to select use object transform and then rewind the simulation, and we should be able to see those are now nicely sitting above the ground plane. So what am I going to do about switching from this animated set of boxes to boxes which are being simulated using an RBD solver? Well, what I'd like to do is switch from the animation to the simulation at the point at which these boxes have reached their maximum velocity and are starting to slow down again. So in order to do that, I'm going to have to measure their acceleration. And although we get velocity data for free coming in through this point pos node, we're not going to get acceleration data. The acceleration data we're going to need to calculate ourselves, but fortunately that's not terribly difficult. First thing I'm going to do is lay down a modify data node, and the purpose of this is going to be to set up a couple of variables that we're going to use in the rest of this network. And I'm going to put them into the point position, which is the arbitrary data container that we've been using. And I'm going to create two variables. An old velocity variable, which is going to be a vector, and in DOPS, slightly counterintuitively, vectors and quaternions and matrices and so on defined using a string notation. So I need to enclose in square brackets 3 zeros like that, and that will set up a variable called oldVal, which is initially set to 0. But in fact I want to set up a second variable, which I'm going to call solve type. And this can stay as a float, and it can have the initial value of 0.